non-stationary signals, some more advanced and robust tools are needed to provide simultaneous signal representation in the joint time-frequency domain. Here, this figure shows the ideal time-frequency representation for our two-component signal example, where we can clearly see the instantaneous frequencies of these components. Of course, this representation is ideal and is obtained by analytical expressions, and therefore it cannot be used in practical applications. That's why some numerical methods for time frequency representations are developed, and they may be divided into two categories. The first one are linear time frequency distributions that provide us signal decomposition into the elementary components well localized time and frequency, and these are some classical approaches. But on the other hand, we also have some quadratic time frequency distributions or TFDs that provide us insight into the signal's energy distribution as a function of both time and frequency. And the special type of these TFDs are the so-called Cohen's class distributions that are characterized by time and frequency covariance, and they possess many useful mathematical properties for non-stationary signal analysis. And these distributions were focus of this research. So in the next few slides, we will just see which distributions we used in this research. First of all, we defined the short time Fourier transform that provides us time-dependent frequency spectrum of the signal by calculating the local frequency spectrum on the sliding window. Spectrogram is the first used time frequency representation, which was obtained as a quadratic model of the STFT. And the spectrogram has very low interference terms, but on the other hand, it has a poor time frequency resolution property where it cannot achieve simultaneously good resolution both in time and frequency. And of course, for each distribution we will see on these slides, we also give how does it look for our two-component signal example. This poor time frequency resolution property of the spectrogram is the main motivation for the development of the alternative quadratic distributions from the Cohen's class. The main representative of this class is the Wigner-Will distribution, obtained as the Fourier transform of the instantaneous autocorrelation function of the signal. And this distribution has excellent time frequency resolution, but due to its quadratic nature, some of interference terms are also called cross terms, naturally arise between the true signal components, and these cross terms make it difficult to interpret these time frequency representations. And this is the reason why all the other one distribution we will see aim to suppress these interference terms, but simultaneously to maintain this good time frequency resolution of the Wigner-Will distribution. And it is achieved by smoothing the Wigner-Will distribution using special kernel functions. And we always have a trade-off between the time frequency resolution and suppression of interference terms. So the first one is the pseudo-Wigner-Will distribution that additionally applies a time window that smooths the Wigner-Will distribution in the frequency direction, and it suppresses those cross terms oscillating in the frequency direction, but simultaneously decreases the frequency resolution of the auto terms. The next one is the smooth pseudo-Wigner-Will distribution that additionally suppresses those cross terms oscillating in the time direction using another time window G, and it allows us to independently control the level of time and frequency smoothing by controlling these window sizes. Next is the Choi-Williams distribution, which is a reduced interference distribution designed with a special exponential kernel function in the ambiguity function domain, where we can control the width of this kernel and control the trade-off between the time frequency resolution and the suppression of interference terms. This distribution has a slow decaying kernel, and that's why it does not suppress well the low frequency cross terms. This is solved by applying its upgrade called the Butterworth distribution, which suppresses these terms by using the low-pass Butterworth filter in the ambiguity domain. Another distribution we used was the Born-Jordan distribution, which has a narrow sinc kernel in the ambiguity domain, and due to this narrow kernel, it suppresses well the interference terms, but loses some of its time frequency resolutions, which is solved by using its upgrade called the Zhao Atlas Marks distribution that additionally smooths this Born-Jordan distribution in the frequency domain. And this distribution achieves very good time frequency resolution and suppression of these cross terms. We also used 4 reduced interference distributions with special kernel functions. And all of these 4 distributions achieve similar results with very high time frequency resolution and good suppression of these cross terms. These were distribution with a kernel based on the Bessel function. Next, we have a kernel based on the binomial coefficients and a kernel based on the Henning window. And finally, we have a kernel based on the triangular window. So we come to the second part of this research, that was the applying of machine learning, or to be more concrete, deep learning techniques, where we focused on the special type of artificial neural networks called convolutional neural networks, because they are specially designed to deal with multidimensional input data, and today they achieve state-of-the-art performances in image recognition and classification. That brings us to the main research objectives of this study. Taking into account mathematical properties of the TFDs from Cohen's class, which we saw that were beneficial for non-stationary signal analysis and representations, we wanted to utilize these good properties and combine them with today's state-of-the-art deep learning classifiers based on the 2-dimensional deep convolutional neural networks to detect non-stationary signals, and apply this method also for detecting binary black hole gravitational wave signals in intensive real-life noise from LIGO detectors. The main hypothesis was that this will allow us to achieve the high performance detection, and we also expected, because of these TFDs providing us high resolution and better structured information and more intelligible representation than the time series themselves, we expected to achieve higher classification performances than the models, deep learning models using only time series data. And here is the main part of the presentation, and it is the proposed method for detecting gravitational wave signals. As we can see from this flow diagram, this procedure consists of 3 main parts. The first part is preparation of data. Next one is the training and testing of deep learning models. And the third part was the performance evaluation. During the data preparation, we collected real-life recordings from LIGO detector and conducted gravitational waveform simulations. These data were then pre-processed, and to this time series data, we applied these 12 time frequency distributions from Cohen's class. In this way, we obtained 12 different data sets that we used as input to 3 different state-of-the-art CNN architectures. In this way, we obtained a total of 36 TFD CNN models, and after training and testing of all these models, we performed evaluation of the obtained performances using several evaluation metrics, and we also compared the obtained performance with the one obtained by the baseline CNN model trained only on the time series data. And of course, in the end, we conducted a statistical significance test based on the Nemmer's test to see whether these obtained differences in the results were statistically significant. So now we will say just a few words about each of these steps. During the data generation, we collected noise data from LIGO detectors. For each data segment, we randomly selected the noise data segment, evaluated its quality, extracted it, and downsampled it to 2048 Hz. And in parallel to this, we also conducted gravitational waveform simulations, from which we obtained the noise-free gravitational wave signals. And of course, before injection into the background noise, we scaled each signal to obtain data examples with a range of SNR, where the optimal match filter SNR of this one detector data was in the range between 0 and 30 decibels. So after injecting the simulated signal into background noise, we conducted a pre-processing procedure consisting of widening in the frequency domain and high-pass filtering at 20 Hz. And in this way, we obtained the time series data examples. And by repeating this procedure, we obtained a total of 100,000 different data examples. So in these slides, we give just a few randomly selected data time series data examples to see how they look like. So this slide shows the noise data example, where the first figure is the original noise from the detector, and the second one is the noise after the pre-processing. This slide shows the time series data example, which contains gravitational wave simulated noise with the optimal match filter SNR of 6.55 decibels, where the first figure shows the original noise, the second one is the noise-free gravitational wave signal, the third one is signal obtained after adding noise and simulated signal, and the fourth one finally is the pre-processed noisy gravitational wave signal. This slide shows the same for the SNR of 14.92 decibels, and this is for 25.82 decibels. And we can visually see from these slides that using only time series data representation, that is very difficult to detect the gravitational wave signals in this time series. And it is difficult to distinguish between those examples containing only noise and those containing gravitational wave signals even after pre-processing. So the next step was to calculate TFDs from these 100,000 data examples, where we first applied the Hilbert transform to obtain the analytical signals, and then calculated these 12 quadratic TFDs. And this, in this way, we obtained 12 different data sets, each containing 100,000 TFD images. So in total, we had 1.2 million TFD images, and these slides show how these TFDs look for the previously shown time series data examples. So here we can see the TFD for data example containing only noise. Here are TFDs for the data example with the SNR of 6.55 decibels. These are for the SNR of 14.92 decibels, and this is for the SNR of 25.82 decibels. And from these figures, we can see that it's more easier to detect those examples that contain gravitational wave signals, as we can clearly see this characteristic chirp waveform. And that is why we expected that by combining it with deep learning techniques, it will be possible to achieve high classification performance even at the low SNR values. So we used these 12 data sets of the TFD images as input to the deep learning models based on 3 different CNN architectures. These were the ResNet 101, Exception, and EfficientNet. And the output of the CNN models, we obtained the probability that the input image contains the gravitational wave signal. So now just a few words about the utilized CNN architectures. The first one was the ResNet 101, which is characterized by the residual or shortcut connections that enabled training of very deep CNN architectures by lowering the impact of the vanishing gradient problem. And the main architecture used is shown here. It has a total of 101 convolutional layers divided into 4 groups, each containing a different number of these bottleneck blocks, which have 3 layers performing 1 times 1 and 3 times 3 convolutions. The second architecture was the exception, which is entirely based on the depth-wise separable convolutions illustrated at this figure. And these convolutions consist of the point-wise convolution, which reduces the input number of channels, and then the depth-wise convolution as a 3 times 3 spatial convolution is applied to each channel separately, and this significantly reduces the number of mathematical operations. The main architecture of this exception network is shown here. It consists of three main parts, and these are the entry, middle, and exit flow. It contains a total of 36 convolutional layers divided into these 14 modules, where each module except the first and the last one also contains these residual or shortcut connections. Moreover, only the first module uses traditional 3x3 convolutions, while all other use the depth-wise separable convolutions with also 3x3 convolutional kernels. And the last used architecture was the efficient net, which represents the current state of the art in this field. This is a method that introduced the compound scaling method into scaling CNNs. In this method, all three dimensions, which are the width, depth, and the resolution, are scaled simultaneously using a factor based on the compound coefficient. The main building block of these networks is the so-called mobile inverted bottleneck convolution block, or MBCOM, shown here, which consists of applying the pointwise, depthwise, and again the pointwise convolution, and it also has a shortcut connection between these bottleneck layers. Another thing is the squeeze and excitation optimization, which is used to recalibrate these initial feature maps in the way that the more informative features are emphasized and those with less information are suppressed. And it is achieved by calculating global statistical descriptors and using them as input to two fully connected neural network layers and obtaining the learned weights at the output. The main architecture of this efficient network is shown here. It uses MBCOM1 and MBCOM6 blocks with 3x3 and 5x5 convolutional kernels. Finally, we also compared the performance of the proposed method based on two-dimensional convolutional neural networks to the baseline model, which was adapted one-dimensional CNN found in this article from 2018, which achieved very high classification performances in detecting binary black hole gravitational waves. And this method is one-dimensional CNN that uses input vector of size 1024. So here we come to the main obtained results. We can see that we achieved very high values of classification accuracy, which was in the range between 96.54% obtained for the Wigner-Weil distribution and the ResNet 101 architecture to 97.1% obtained for the spectrogram and efficient net. Moreover, as the baseline model achieved the classification accuracy of 93.15%, these methods outperformed the baseline model by 3.39 to 3.95%. The second metric was the area under receiver operating characteristic curve, which was also very high in the range between 0.985 to 0.989 obtained for the distribution with a triangular window and efficient net, and the Choi-Williams distribution and efficient net architecture, respectively. And these values were also for 1.72 to 2.07% higher than those of the baseline model. And we can see, as we are already in the very high accuracy range, that these improvements represent a very significant improvement. The same is true for other considered metrics, which are given here. These were the recall and precision. And also we analyzed the F1 score and the area under precision recall curves. All these metrics achieved very high values and outperformed the baseline model. For more detailed analysis, we also use some additional performance metrics. Here are on these slides, they are given only for the baseline model, and for 3 TFD CNN models that achieved the highest accuracy for each CNN architectures. Those were the Choi-Williams distribution and ResNet 101, Wigner-Weil distribution and exception, and the spectrogram and efficient net combination. And from these confusion matrices, we can see that the proposed method achieves very high classification performances and outperforms the baseline model. The same is true for these receiver operating characteristic curves, and finally for these precision recall curves. To conclude this presentation, we can just sum up that in this research, we developed a method for detecting binary black hole gravitational wave signals based on deep CNNs and quadratic TFDs from Cohen's class. And using this method, we achieve very high classification performances, which are also higher than the method using the time series data. There are several ideas for future work. Two of them are given here. So the first one on which we are working is development of novel modification of TFD from Cohen class, which should be more robust to noise and interferences, and then applying this developed method to this procedure of detecting gravitational wave signals. And the second one is to apply data-driven locally adaptive denoising technique to this data prior to the detection procedure to see whether it should achieve higher classification than now. This is also based on our previous research where we applied our proposed method based on local polynomial approximation and relative intersection of confidence intervals to denoising gravitational wave signals and achieved very good results. So this research is based, this presentation was based on the research presented in our publications in IEEE Access published this year, and also in my doctoral dissertation defended a month ago. And also the second part considering the denoising of gravitational wave signals is available in these two articles. Here are some main references used for preparing this presentation, and we have come to the end of the presentation, and thank you very much for your attention.
Other questions? Okay. You say a little bit more about the signal and noise populations for those metrics that you present at the end?
I'm sorry, can you repeat? I didn't quite hear you.
Is this better? Am I loud enough? I think it's on. I'll just try to speak louder as well, so if anyone else gets painful. For the metrics that you present at the end, could you say a little bit more about what signal and noise distributions you use for that?
For which one?
In general, like what your testing case is.
Okay. The noise was data from O2 run from LIGO detectors, and we used the SNR range between 0 and 30 optimal match filter SNR.
Sorry, could you repeat those numbers to the SNR?
I'm sorry, something is interrupting. I don't.
I'm not sure if this microphone is actually taking, properly. Can you hear me?
I can hear Michael, but I can't hear the question. Yeah.
So maybe we can use this microphone. Maybe this is working.
Yes, thank you. I think you were answering exactly what I was asking. I just didn't understand the numbers of the SNR. So if you could repeat them once more, thank you.
I have a feeling that maybe the microphone is somewhere here, and these are not really working. Only working in the room, but not really are connected.
I can clearly hear you, but I couldn't hear a question. I can clearly hear you now, but I don't hear a question.
I think the question was about the range of signal to noise ratios that you have used in your analysis. because that would also be my question, because you shown these plots that show the, for example, receiver operator cross characteristics, but they were not plotted in the as a function of SNR, for example.
Yeah, we didn't. I don't have now this analysis for the how this changes with SNR level. I have just a total in a total range. Accuracy and receiver operating characteristic, everything is calculated in a total range of the data set we tested on.
Okay, so just to conclude with the question about the SNR, what's the total range between what value and what other value?
Between 8 and 30 decibels optimal match filter SNR.
Okay. 8 and 30. Okay. Thank you very much. Are there some other questions?
Thank you.
I don't see any questions or some comments. I have a comment. This is a very nice work. I was waiting for these results. I remember that we talked about that in one of the working group meetings, and now it seems that we have completed this. Very nice. Okay, so if there are other comments or questions, then thank you very much, and we can move to this last topic of today, which is discussion of the G2net all groups paper. Oh, by the way, I didn't ask if there are some questions from the remote, because maybe there are, but I don't see any comments or hands up. No questions. Okay, good. No, but we have to live with that. Okay, so last point is oops. Oh, okay. Last point is our work in progress. So let me try to share what we have. And basically that point is basically to start a discussion. How do I share this? Yeah. It's okay. It's okay. You can just share this. Yeah. I just wanted to share this. We're already sharing, but I want just to share this. Okay. So I'm sharing the PDF of what was I took it today from the overleaf, and basically. So this is a document that is very much in progress. The idea is such that we already have a review paper that basically reviewed the applications of machine learning to gravitational wave astronomy that was led by Elena, and it was written in 2020. This paper has a different goal. The goal would be to summarize and also, I think, in my opinion, it would be very nice to give some sort of a direction outlook of what we did and what we think is useful and what we want to do in the future based on what we did in G2net action, in this cost action. So far the paper is basically structured like that we have to write an introduction that basically lays down all fundamentals and explains why this is important. And then basically the working groups describe their results. So this is already somehow done. Several people already contributed to this. Many things. So this is divided in several kind of pieces. So signal detection in general, also denoising, denoising of gravitational wave signals, some other algorithms like detecting glitches and glitches characterization, anomaly detection, which is also a way of detecting things, but not in this kind of classic classifier, but it could also be used for glitches. and other topics. And as you see, it's not fully kind of set yet, because we have different topics. So I would like, and also this part is important. This is an application of, I mean, so this is slightly different direction, because it also goes, we can also go, and some of us are going to the direction of actually providing fast production of waveforms, for example. So these are the surrogate models of gravitational waveforms that are used to parameter estimation, because you have to produce a lot of them to find the best model at the end if we find that if we detect something. So so this opens my first point, that is, what should we still add? If you have something to add, please consider adding it to this paper, and then we have to somehow on this with using the complete list of things, somehow put it in order or in some kind of way into the paper, and then show that it is structured and it leads somewhere in some way. Okay. Second part is this machine learning for geophysics. So this is the working group 2, and there is also working group 3, machine learning for control systems, that I hope will be filled by other working groups. But and then, so first of all, we have to agree what we want to do as working group 1, and then we have to agree with other working groups what we want to do with them together to write the summary and some sort of an output. That is my naive idea of how this paper should look like, but maybe you have other ideas. And also, I invite people from the remote to also comment on this.
So most people will be able to hear me, or should we just come up front when we have a call?
I don't know. Remote people, can you hear us?
So it's a very, very naive question, because I probably get to start of discussing of this paper. Of these sections are like almost abstracts of other works, like there's a list of people and so on. Is that the way we should contribute, and then it will be merged into like a more consistent text at the end, or will it actually look like this with these?
So far it was something like a list of projects or ideas that people would like to contribute, and so as far as I see, it really moved very far from that idea. But I would not like to be a list of things. Yeah?
Just speaking louder, but it seems they can't hear you.
Okay. So I think maybe, because I have a feeling that the microphone is somewhere here. Sorry, but
I mean, there is a microphone here in the camera.
Yes,
so
I think this
you should be able, but anyway, with this one, yes. And you can change from this is the chat, and then you can go to the paper here, okay?
Mm-hmm.
Sorry.
Okay, so but we could also hear David, so it's not. This is very pretty, but maybe I will change this. Yes, so far it was just a list of projects that we have already finished, or at least they may be finished in the foreseeable future. But at the end, we cannot leave it as a list of projects. We need to somehow combine this and produce something more with another value, I guess. Of course, it could be a list of, it could be some sort of a review, a list of finished projects and so on, but it may be better to do it maybe slightly better, slightly more out of it. And I think there is still time for everybody who didn't join to still join, because we still have a few months today. And then I think something that could be really useful would be to fantasize a little bit about what we already did and how what we did could benefit in the future. And this is maybe less strict, but I guess it might be useful, because it would also show that we have some ideas that can be based on what we did. This is to be discussed. Maybe you can come here and speak to this thing, because I guess that's the thing. There is a There is a source here. No, I think the microphone is somewhere in this box.
Aha, so to find microphone, huh? Talk to the box. Is it the plan to have total review of all of the fields, or just about the topics which are done within our action?
I think the idea was about writing a paper at the end of the action time of our project time that would summarize what we did and what we still think is useful, just for the future and something like that. So that would not be a review about everything, but only what we were thinking of, we were involved in, so on and so on, this type of things.
Okay, but is it idea to have separate sessions for separate working groups, or to have,
yes,
or to divide the papers into models and methods, something
that's a very good point. So far, it was simply divided into 3 working groups, but maybe actually it's not a proper approach. Maybe we should actually divide across this different line, like a different line, which means methods or goals or something else. Something not simply by working.
Go with first section model, second section methods, and then in third to merge them. Apply techniques.
Yes, but also we could do it like it is now, and then have a section in which we explain that this different projects have used the same methods, and the other different projects have used different methods, but are they're the same goal, and so on. So this is in some sense a technical problem, but we have to decide, because at some point we have to start writing this one way or the other.
So now is the phase of collecting the abstracts,
yes.
and after that
Yes.
we'll be merging the abstracts, and then
Yes,
this question could be asked.
I mean, in the time of collecting abstracts, we already have to have, we need to have some sort of an idea what is the next step, right? Because it will not work in such a way that we'll collect abstracts or collect ideas, and then magically the paper will turn out. At the end, right? We have to have an idea, how to do it. At least I think we have to. So that's the open question, and this question, I think, is both to us and to the whole collaboration, because we need to combine these 3 working groups results into one paper. Of course, we are the biggest group, so in some sense we have a lot to contribute. But that doesn't mean that the other groups cannot contribute equally, right? Even if they have somehow less papers, something like that, doesn't matter. But we can provide this picture somehow. So I would like to know your opinion about that. Are there some other questions or comments in the chat? Please don't hesitate to speak. Hello, remote. Okay, so if there are no comments now, of course, it doesn't matter. It doesn't mean that we cannot come back to this, but I think we have to already start thinking about well, the passage of time and so on. And David has a comment.
So I think that's an extremely good point of how to structure it, if by method or if by topic. I don't really know enough about the other working groups, but even within gw1, we could already say CBC detection, CBC parameter burst, and so on, or sort by CNN, whatever. And actually, do we have chalk somewhere? Can I put something on the board?
Yeah, sure.
I'm actually thinking we could have a table or a picture somewhere that says on the one axis method, on the one axis topic. So we CNN, again, and whatever. This would be PDC, CW, controls, whatever. And then we have like a course here, a course here, a course there. And basically the empty parts of that graph are your plan for the future, what still needs to be done, things that haven't been tried. And we just have to decide on one of the axes for the actual structuring of the paper, but sort of the reverse lookup could be done by that paper. I can tell you're not listening.
Sorry, I wanted to switch to whatever, but
I was suggesting we can somewhere have a plot or table like this that says what has already been done, and sort of the empty space of it is almost writing your future section for us. And then we can either sort it by topic or by method in the paper, but people can look up the other direction. What someone would have in the end when all the contributions are in, populate this only.
Yeah, I am afraid that this will be very complicated.
It might be, like, but it could be a good tool to structure
yes,
this.
We could do that for us just to see what was really done in this type of plot, yes. Structuring this knowledge.
But for now, I guess if someone like me and my group, we haven't contributed anything yet, the easiest is if we just add a paragraph with names and a topic somewhere, and then it gets moved around later, right?
Yes, yes. I think this. I think this doesn't necessarily have to be some kind of published work. I mean, if you're already talking about this, so this is already a result, right? There are already some results. They don't have to be published in a journal. They can be just results. And I think also computer science doesn't work like we work in astrophysics. They don't publish things so often. Basically, they publish things on blogs because everything is changing so fast. Something that would be interesting is, for example, yeah, these things of transfer learning, new approaches. What Nicola was presenting now is like this approach of using something off shelf. I mean, directly from the shelf, like exception or something that already was brought on something else to our problems and assigning the value of this, this ready-made solutions, because we have at least I remember this from astrophysics, that we tend to invent everything from scratch, right? But maybe we should not, right? This is a kind of a combination of applied science and other things. So this could also be discussed, because we have to think about this work as some sort of a useful guide, right? Because for us also, because maybe we'll try to have another action or something similar in the future. So it will be it is a little bit like a diary, or we did something, right? And we want to go to the next step. Okay.
If you could go to the title once again, please. So, what is the state of the art of reviews in this direction? How many review papers is there on machine learning for gravitational waves, machine learning for astrophysics?
So this you mentioned this paper of Elena.
Yes, beside right? This paper.
Yes. So I think this is still something that is quite recent and quite up to date. I'm not aware of something similar.
Okay. How is this paper organized with respect to this?
So this paper, the paper from 2020 was basically something like a list of things that were done. It was divided by methods, maybe slightly about sources, but to me it was a little bit too dry in some sense, if I may. It's not a criticism. It was just what was done already, and it's very useful, of course.
So gravitational detection methods for detecting gravitation.
Not only detection, it's about more than just detection. Parameter estimation, processing, all kinds of things. But yeah, so because it was also about detector characterization things. But here maybe, I mean, of course, we may do it something like that. What we did will be also very useful. But maybe we want to do something more than just review recent review of things that were done. Maybe we would like to, yeah, do something else. That's the open question.
We're going to read this paper. People from computer science, or people from astrophysics, or people from geophysics, or people.
I think that the people who are interested in application of machine learning to their fields, yeah. Surely gravitational wave physics is interested in this. So I hope people, young people, for example, will be reading this and then they will be becoming our colleagues, right? Because they are interested, they would be interested in this. At least I hope, right? Because I mean, if you're starting a field, you would like to have some kind of a presentation of what was done, what will be done. Is it an interesting field to join or not? Because maybe not. Maybe it looks interesting, but it's not. If we write a section in the sense like open questions, right? We didn't solve this because we think that it's interesting, but it was more complicated than we thought, blah, blah, right? Usually we don't write anything. Hello? Yes? There was someone from the remote, but I couldn't hear exactly. Wait. Sorry?
Maybe a mistake.
So wait. Okay, so I think that. So we don't often mention things that didn't work. For example, I'm not saying that we should do it here, but I would like to have a kind of a subsection that says these are important unsolved problems that should be attacked. Because, for example, we cannot do it because we don't have computing power and we don't have good ideas, or the problem is too complex and we need really fundamental new ideas and things like that. And I think that would be really inspiring. Not just a dry list of things that were done, but also future things.
Maybe also a section about data, how to collect data. We had several workshops in this direction about like data. If someone is not familiar with gravitational waves at all, not familiar with data at all, but he is good in machine learning, we want once he read the paper to be able to suggest some solution.
Well, I mean, that would probably be too broad because we are really focusing on already collected data and maybe processing the data, right? Because we entering this too deeply into the detector part. Maybe it's too much. And also, I don't know if this is what we really did.
No, but it was opposite what I said. If we give the paper to someone who is purely from machine learning, he has to know how to access the data and to try his ideas. Yeah,
definitely. Part of one of the tasks of the working group 1 is access to the data. Yeah, we can describe this for sure. It's not very complicated. And there are already several demonstrations of people really accessing the data and using them. No problem. So that's the idea. And I don't know if we'll really solve answer all any question today, but this is just like a call to start thinking about this because it would be good to have this. So what do you think? Maybe you don't have anything to say now, but please remember about that, because I guess this will be quite a pleasant work, I would say, because we have really quite a lot of nice results. It's nice to describe them. It's nice to think about them, for the future, what they really mean, and how can they be used in the next possible next project that we may have. Okay. I don't see anybody from the remote to comment this. So I don't know if there are no other questions. There are no other comments or questions. Maybe.
I think that's a nice stand.
Okay. Annalisa?
Yes. Can you hear me?
Yes. Yes.
Michael, we already discussed this, but do you think that we can ask more coordination to Elena about this topic? Because probably if she will define some bibliography for the different sections, it would be simpler also for us to state, okay, I will contribute to this section, because in several cases it means reading the paper and summarizing it, because this is mainly a survey paper. But probably it would be nice if Elena or someone else, or Elena with another team, can help people providing the bibliography of this survey. I don't know. What do you think about suggesting her this direction?
I thought that we should be this team because I would not like I would not like Elena to tell us what to do. We need to know what we want to do, right? We maybe know we want to maybe do many things. We just need to decide what we really want to do, and especially what to do with data that we have obtained by our group, right? Because I guess Elena will not tell us this. We need to know, I think.
Okay, I think that the problem here is the coordination, because without a coordination it's difficult to understand, okay, I want to do this, because we are also all very busy, I suppose, and so it's quite difficult to say, okay, I will be in charge of this. Probably it's simpler if someone assigns tasks.
Yes, but I guess Elena is the busiest of us. That's also the problem.
So you're just to have a proposal. We are posing the problem now, and as a working group 1, we can set that in one of our monthly meeting. Now we know the problem, and we start stating that if we put our name in the list, we want to contribute to that section. I don't know if this is too hard as a constraint, but probably we need. But I'm stating also for myself, not because also I am also busy with a lot of duties in the university, so it may be difficult to contribute. But in that case, my name should be removed. So I think that at this point we need something in this direction. In the working group 1, these people intended to contribute, and the name is reported in the list because these people will contribute to these sections.
Yes, well, you're perfectly right that we didn't really discuss this really like that. We just said that, yeah, there is this idea about the working group paper, or like a G2net working groups paper. And then that was basically just an announcement that this idea is kind of floating around. But now we are actually discussing how to do it. I mean, not maybe also a little bit maybe about what to do, but also how. And so now we have to really think about it. I don't expect that we will now have a magical solution today, but we need to really start thinking about if we really want to do it, because it will not be done by itself. I don't believe that.
Sure. I agree.
But
I agree with you.
So this may look a little bit like a chaotic discussion, and that nobody knows anything, but we already have a lot of things done in this job. There is some kind of a structure. Maybe it has to be a little bit restructured, and we are not starting with zero. We were starting with a lot of input, and maybe even that's the problem. Maybe we working group 1 has too much input, and we have to think how to approach this. For example, if I have collected is maybe the big word, but I looked at the NASA ADS list of papers that cite our action in the acknowledgements, more than 60 papers. And there are different papers really concerning detection, concerning detector characterization, data processing, parameter estimations, this waveform model surrogate production. So basically things that are kind of on the side of parameter estimation and so on. There is a lot of activity in various fields. Now we have to somehow have a picture idea how to present this in this review or in this paper. So if you go into the today's presentation, this first presentation at the beginning, there is a link you can follow, and you can basically see a lot of papers. And so it's not clear what they really how to look at this as a collection of papers, but I hope we'll see some sort of an order or some kind of a clear picture will emerge from this. Yeah. Okay. Are there some other comments or questions, either from the room or from the remote outside? Oh, Vladimir. Yes.
Does it make sense to pick up all the abstracts from our web page? There is a list of titles that acknowledges our action, and to pick up all abstracts, put them in one document, and then automatically see the frequencies of appearance of particular keywords, and then we will maybe figure out what should be the sessions, what is the core of our research.
I think, well, I don't know if such a completely automatic approach will work, but anyway, we have to have a look at what we did and what we still plan to do, what we are doing now, what we did and didn't work, what we thought was promising and wasn't promising at the end, this type of things. I imagine that this paper would be about this, because at the end we are on the other side of, we're almost finishing with the action. We will be writing some sort of a final report. This is kind of like a final report, right? So that we promised to deliver something. We delivered something. This is maybe not exactly what we were thinking we will deliver, but we also maybe over-delivered because we did more than we thought, and so on. So yeah, something like this. Yeah. Okay. So, and with this, perhaps I will finish my sermon as your priest and so on, because we already had a busy day. We can continue this discussion over a few days, next days, and then we'll meet on the again on this Work Group 1 meeting in a month and talk about this again. Yeah. So if there are no other comments or questions to this, let's close the session for today, and we'll continue the discussion over dinner and so on. Thank you very much. Okay, so we are closing for today, and we'll meet. This is also a message to the remote people, and we will start at 9:30 tomorrow with talks. Thank you very much.